Geodesics in Negative Curvature. It's one of the first papers where you can begin to understand what chaos theory is. Hadamard is a very famous mathematician. I would say mathematicians during, I have to admit, during many years, I had listened to his name so many times that I was convinced that there were two Hadamard. He had a long life. I was convinced that there was the father and the son, but no, there was only one Hadamard. Hadamard made a lot of contribution in mathematics. I chose here a few of them. At the beginning of his career, he was number theoretical minded. He was one of those who proved the fundamental theorem about prime numbers. Then I want to emphasize his book in 1898. This is the book called Leçons de géométrie élémentaire. This is a wonderful book for secondary school. He spent a long time trying to polish the best possible book for geometry in secondary school. You have to know that at the beginning of the 20th century, there was a big bifurcation in the teaching system in France. Before, in the 19th century, every talented student would go to humanity. At some moment, two people, basically Poincaré and Hadamard, decided to convince the Minister of Education that there should be a way for scientists and a way for humanity. And Hadamard wrote this book in order to teach good mathematics to students who would go to mathematics later on. And then he became an analyst. These kind of things happen. And you can see that he wrote this book on PDE in 1964. As far as I know, this is not his best contribution. And I want also to mention his wonderful book, Essai sur la psychologie de l'invention dans le domaine mathématique, which is something which is very well known. And if you don't know it, you have to read it. It's trying to understand what's happening in your head. This is a very interesting book. Anyway, I recommend strongly this biography of Hadamard. This is one of the best mixture of history and mathematics. This book is full of mathematics and full of history, and everything is mixed. Usually when you have a book of history of mathematics, you feel in bad mood because you have not enough mathematics to eat. But this book is full of mathematics, and you can learn a lot of things about PDEs, for example. I learned a lot of things about PDE. Anyway, so today I want to discuss this paper of Hadamard, but first I want to explain his motivation. And this motivation is not written in the paper, but it's obvious that it was his main motivation. And the motivation comes from mechanics and celestial mechanics. There is this fact from classical mechanics, rational mechanics, which is the following. If you take, let's say, a potential function in the plane, V, and you look at the motion of a point which is submitted to the force, which is the gradient of the potential, and you look at the trajectory of the point under this force. And it's well known that there's a preservation of energy. Energy is the sum of the potential energy and the kinetic energy. This is constant. You fix that constant. And Maupertuis and Jacobi understood the following geometric fact, that if you fix the total energy E, and if you rescale the metric in the plane, ds, by the square root of E minus the potential, you get a Riemannian metric in a domain in the plane, in the domain limited by V of Q less than E. And the equations of mechanics tell you that the motion of the point is exactly the motion of a geodesic on this Riemannian metric. So there's a perfect dictionary between geometry, the behavior of geodesics, and dynamics, the behavior of a point under a force, under the gradient of a force. And so, in the mind of Hadamard, when he discusses geodesics, he has in mind mechanics. And moreover, the mechanics that he has in mind is very specific. It's probably around the three-body problem. So the three-body problem is the following question from mechanics, which is still open today and very interesting today. You have a body, a mass like the sun, and then you have another mass like Jupiter, for example, and you assume that both are rotating at constant velocity on circles around the center of mass. And then you add a third mass, which is very, very small, which is infinitesimally small, and this third mass is attracted by both masses, the sun and Jupiter. And you want to understand the motion of the third mass under the two main forces from the sun and from Jupiter. And of course, since the two main bodies are rotating, the good idea is to write the equations of the motion not in a standard coordinate system, but in a rotating coordinate system in which the two bodies that you can see here, the yellow point and the dark point, are fixed. And then it's a matter of computation, and not only computation, but also understanding that in this rotating system, the third body is following some kind of gradient of a potential. You can see the potential at three terms. One is the Newtonian potential from the main star. The second is the Newtonian potential from Jupiter. And the third, 1/2 of x squared plus y squared, is the potential coming from the centrifugal force. Anyway, if you want to understand the motion, the three-body problem, you immediately arrive in the previous question, try to understand the geodesics on some surface. So that's no doubt the motivation of Hadamard in his paper. And before I explain the content of the paper of Hadamard, let me show you not the paper itself, but the referee report. So the referee was named Poincaré. Poincaré was about 10 years older than Hadamard, and he wrote a report on the memoir. This is published in the, at the time, at the time when you would submit a manuscript or memoir to the Académie des Sciences, they would send it to some academician, he would read it, he would comment on it, and they would publish the commentary, if positive. He's positive. Anyway, this is an extract from the report from Poincaré, and immediately Poincaré understands what's going on. He says what Hadamard is not saying. He says the property of geodesic lines deserve attention of geometers. They are simpler than problems from dynamics, but they contain all the difficulty of the mechanical question. So he explains the motivation of Hadamard, and then he explains the main result of Hadamard. I will tell you now. And what is interesting is that he complains that Hadamard has chosen the wrong hypothesis. As you will see, the hypothesis of Hadamard is that the corresponding Riemannian metric on the surface that you are studying has negative curvature. And Poincaré says this is wrong. We have to look at positive curvature. The good question from celestial mechanics is not negative curvature, is positive curvature. And you will see tomorrow, in the talk that I will give tomorrow, the answer from Poincaré. He wrote a paper 10 years later in which he discusses the positive curvature case, and he explains why this is more interesting in positive than negative. Anyway, he's kind of nice. il peut ainsi arriver à des résultats complets qui sont exposés dans le travail soumis au jugement de l'Académie. Then he gives in one page a good summary of the paper of Hadamard, and then he says, well, we should accept the paper. And the paper was accepted. Okay, so let's go and have a look at the content of the paper. The idea of Hadamard is to discuss geodesics in negatively curved surfaces. First, you have to find examples. You know, at the time, mathematicians were used to look for examples first. Bourbaki was not born. And he begins the paper by constructing examples, and he says, look at that. Let us look at a certain number of points in the plane, and you take the distances of a point, moving point x to P1, P2, Pk. You call the distances delta 1, delta 2, delta k, and you write an equation like that. The surface z is equal to log of delta 1, delta m divided by delta m plus 1, delta m. And he says this is a surface, and he says this has negative curvature. And here's the picture. When you take the log of delta 1 over delta 2 for 2 points, you get a picture like that with 2 poles corresponding to P1 and P2. And he says, oh, it is obviously negative curvature. Can anyone tell me why this is obvious? Why is it obvious that the graph of this function, log of delta 1 delta m divided by delta m plus 1 delta n, is negatively curved? Well. Hadamard says, of course, it's the real part of a holomorphic function. Therefore, it's harmonic. And the graph of a harmonic function is negatively curved, QED. So he says, okay, we get in this way many examples of negatively curved surfaces, but the bad point of these examples is that they have zero genus. He wanted more examples with more complicated genus. And he constructs more examples, like this one. You see, you have two hyperboloids, and somehow they merged in a connected surface of genus 1. And he says, how can I mix or merge two surfaces with negative curvature to produce another one with negative curvature? And he says, look, if the equation of the first one is u is equal to 0, and the equation of the second one is v is equal to 0, these two surfaces intersect on a curve. Intersection of u is equal to 0 and v is equal to 0. So let's look at uv is equal to epsilon. Then he explains, by simple means, no computations, that in many examples, if you merge two surfaces with negative curvature with this kind of trick, you produce a new surface with negative curvature. So it's a very simple trick of finding examples. So it has many examples of any genus, any number of holes, any number of horns. He's not very satisfied with this kind of picture here. Oops. He's not satisfied with that because the funnel is thinner and thinner. It's like a pole. He wanted to open the funnel. So he takes some kind of dilation on each horizontal plane, and he plays with surfaces without writing a single formula. He produces a huge number of negatively curved surfaces. And then he comes to the core of his paper, trying to understand the behavior of geodesics on such a surface. So this is an example of a so-called pair of pants. negatively curved, and you want to understand geodesics on this pair of paths. The first thing that Hadamard does is to draw on this pair of paths 3 geodesics, closed geodesics, and these 3 geodesics give on the surface a compact domain that I will call the core of the pair of paths. And this is something that is convex inside the surface with negative curvature. And then what Hadamard says is that, look, a geodesic is traveling on the surface. It may go out when it crosses this geodesic, but when it goes out, it will never come back because it's negative curvature, it cannot come back anymore. So geodesics might go out from one of the 3 ends and never come back. Maybe they come from the past, from some end and enter the core, or they may stay their whole life inside the core. And the main point of Hadamard is to try to understand those geodesics which spend their whole life inside this convex part. And he wants to understand if there exist geodesics spending all their life in this domain or not, and to describe them. So the trick is the following. You cut the pair of paths like that, and you decompose it with perpendiculars like you see in dotted lines, and you decompose your pair of paths in 2 hexagons. Let's say, and then if you take your geodesic, it will travel in the surface, and it will cross from time to time. You have 3 lines. Here's one. Here's another one. And the third one is, where is it? Is here. If you take your, let me call it C1, C2, C3. And if you take a geodesic traveling on the surface, it will intersect from time to time C1, C2, C3, in some order. And the main theorem of Hadamard is that any sequence of letters, C1, C2, C3, without consecutive equal letters, arises for some geodesic. So if you give me, for example, C1, C2, C3, C2, C1, C3, and you take this cyclic word, according to Hadamard, there is one and only one geodesic which will cross C1, then cross C2, then cross C3, then cross C2, then C1, then C3, and back again. So there is a bijection between periodic geodesics inside the surface and cyclic word in 3 letters, no 2 consecutive being equal. It's a way of coding geodesics by words. So this is the beginning of what's called symbolic dynamics. He does that for finite periodic sequences. He does not look very much at infinite sequences, but implicitly he uses them. So let me explain something. Basically, he is not putting that explicitly, but he is introducing what's called the shift map. You take the compact set ABC to the Z, and you look at the map which shifts by one coordinate, and the geodesics in the surface are coded by words which no two consecutive symbols equal. That's the main contribution of Hadamard, trying to encode the geodesics through words. Okay, so it's a difficult paper, and this paper has been understood and explained by the famous French philosopher of science, Pierre Duhem, who wrote this book, La théorie physique, son objet, sa structure. It's really a good book about the interplay between mathematics and physics. And there's a full chapter in which he tries to explain the paper of Hadamard to the layman, without formulas, without nothing complicated. And let me show you the beginning of this chapter. He called that an example of a mathematical deduction that can never be utilized. So it's an example of a useless theorem from mathematics. And the researchers of Hadamard provide us with a very striking example of such a deduction that can never be useful. It is borrowed from one of the simplest problems that the least complicated of physical theories, mechanics, has to deal with. And then he describes the experiment of a point moving on the surface, and then he describes the result of Hadamard on periodic trajectories associated to words. And in order to explain that, he has imagination. So he says, imagine the forehead of a bull with the protuberances for which the horns and ears start, and with the collars hollowed out between those protuberances. But elongate these horns and ears without limit so that they extend to infinity. Then you will have one of the surfaces you want to study. So let me show you something. A few years ago, I had the opportunity to produce a mathematical movie on chaos, and one chapter is about that. So I want to show you an extract from this movie, and I will show you the English version, of course. The Brazilian version is much better because it has been recorded by a Brazilian singer. She is called Talma Freitas. And there was a big problem because she's a lady, and Duhem is a man. So how to do? She could not speak at the place of a man. So I decided that I would myself play the role of Mr. Duhem. So, and that was even better, so I could my French accent. And we had the same idea in the English version. You will see that the main speaker is American. And when Duhem is speaking, this is me with my French accent. So this is the bull. Just one comment about that bull. When we produced this movie, we had one principle. We did not want to spend 1 cent. We wanted to do everything ourselves without spending 1 cent of a dollar, nothing. Except that at some point we needed the bull. And believe it or not, you can buy them on internet. It's $25. You pay $25 and you receive the coordinates of 72,000 triangles that you put on your computer, and you get this kind of picture. So this is the only thing that we bought. Okay, so let me...
Listen to Pierre Duhem, the philosopher of science, presenting the work of the mathematician Hadamard, published in 1898 in an article entitled On Geodesic Surfaces with Opposite Curvatures.
A material mass slides on a surface. No gravity, no friction hinders its movement. It describes a line that geometers call a geodesic curve of the surface under consideration. When we choose the initial position of our material point and the direction of its initial velocity, the geodesic is completely defined. Imagine the forehead of a bull with protrusions from which the horns extend, and passages between these protrusions. And let's extend the horns towards infinity. We will then have one of the surfaces that we want to study.
Extend the horns towards infinity? Surely this is some fancy of a mathematician. To imagine launching a ball on the forehead of a bull with infinitely long horns. We will first use a different example, but one that is in the end quite close to Hadamards geodesics, the game of billiards. Here is a rectangular billiard table. I shoot a ball, and then another, almost in the same way. Too simple. The two balls follow trajectories that are very close. Let's add a horn, a circular bumper. Now look at two nearby trajectories. They hit the bumper, and the first goes off in one direction, and the other in a completely different direction. Their futures quickly become very different. Here is an infinite plane where balls can roll without any friction. There are three circular obstacles. Let's call them A, B, and C. Now, it's as if we were observing the geodesics on a surface with three horns. Let's take a ball and shoot it. If we aim well, the trajectory can hit A, then B, then C, then A, then B, then C, and so on. A periodic triangular trajectory. Are there other periodic orbits? Hadamard proves a beautiful theorem. He says that if you choose any word written with the three letters A, B, C, under the condition that consecutive letters are different, for example, AB, ABC, ABC, then there is a unique periodic trajectory that visits the bumpers successively in the order dictated by the word in question. You see the complexity of the situation. For each word, there is a periodic trajectory. And there are lots of words. For example, the word A, B, C, B, C, B, C, B, C, B, C is a trajectory that pretends to hit only B and C, but once every 11 rebounds, it will hit bumper A. Of course, we must aim precisely, very, very precisely. Never to return. Here is Duhem's book.
First, there are geodesics that close on themselves. There are others that, without ever coming back to their starting point, never end up infinitely far away from it. Some keep turning around the right horn, and others around the left. Others, more complicated ones, alternate turns around one horn with turns around the other ones, following certain rules. On our bull's head, there will be geodesics that will go to infinity, one by climbing the right horn, others by climbing the left horn.
Imagine the moon, that has always been the Earth's companion, suddenly deciding to shoot off towards infinity.
Despite this complication, if one knows with an absolute accuracy the initial position of a point on the forehead of this bull and the direction of the initial velocity, then the geodesic that this point will follow during its movement will be unambiguously fixed. It will be quite different if the initial conditions are not known mathematically, but practically.
Appreciate the subtlety, not mathematically, but practically. Watch these geodesics that begin at the same point and start almost in the same directions. They follow almost the same path for a while, and then they separate. The green, red, and blue geodesics have completely different futures.
If a point is launched on the surface in question from a position that is given geometrically, with a speed that is given geometrically, then mathematical deduction can determine the trajectory of this point and determine if this trajectory moves away to infinity or not. But for the physicist, this deduction is forever unusable. So let me tell you something, that the geodesics that you have seen here are actual geodesics. We had to compute the geodesic flow on the bull. So you have the surfaces given by triangles, you have to smooth the triangles, and we solve the differential equation so that this is not fake. I mean, the curves that you have seen are indeed the geodesics on the surface of this animal, $25 animal. Okay, so let me tell you about what happened next after this wonderful paper of Hadamard, which was really at the birth of chaos theory. If you don't know the initial position completely, you might lose any hope of understanding what's happening later. Then you have Morse, 1920. Morse understood very well these combinatorics of words, and unlike Hadamard, who only used finite words for periodic geodesics and combinatorics of finite words, Morse was courageous enough to look at infinite words. And one of his contributions is in this paper, 1920, recurrent geodesics on the surface of negative curvature. And this paper is the birth of something called the Morse 2 sequence. I will say more about it. The idea of Morse is the following. You imagine some transformation T mapping A to AB and B to BA. And you start with A, you get AB, and then A goes to AB, and B goes to BA, and you do it again. So A goes to AB, B goes to BA, B goes to BA, A goes to AB, and you continue in this way an infinite number of times. And you can observe, and this is easy to check, that each time the length of the word is doubled, and that each time the first half of the word coincides with what you had before. So for example, the first half of ABBA is AB, and the first half of ABBABAB is ABBA. So the word is actually growing and produces a word of infinite length. This word is called I will give more detail later, but this word is called the Morse sequence. And Morse proved two things. Well, three things. First of all, he had the idea that indeed you can apply the technique of Hadamard, not for finite words, but for infinite words. And using this kind of word, he could produce a geodesic on the surface, which follows this trajectory. Well, there is a subtlety here. I have only two symbols. I had three symbols, but this is a detail. So this produces a long geodesic, and Morse proved that this infinite word, first of all, is not periodic. That's quite easy. And even more, it does not contain a cube. You cannot find in this word 3 times the same block. So let me explain that quickly. That's very easy. Suppose you want to write a word in A and B, and you are forbidden, you don't want to write squares. So you start with A, and squares are forbidden. So the next letter cannot be A, because otherwise you would have A squared. So you have to be B. The next letter cannot be a B, because you would have a BB. So you have to put A, B, A. And then the next letter cannot be A, because otherwise you would have an A squared, forbidden. So it has to be a B, but you have A, B, A, B. And then you have written a square A, B squared. So any word in A and B has to contain a square. And the question is, does there exist a sequence of letters in A and B that does not contain cubes? Does not contain 3 times the same block. And the theorem of Morse is that this is an example. This sequence of A and B does not contain a cube. Okay. So what's the consequence of that? The consequence of that is that you produce a geodesic on this surface, which is not periodic, because the word is not periodic, but not only that, its closure does not contain a periodic orbit. Because if it contained a periodic orbit, that would mean that the geodesic would be close to a periodic orbit and has to repeat itself a high number of times. So you would find a cube, or maybe the 4th power, or whatever. So if you can prove that this word does not contain a cube, you prove in particular that the corresponding geodesic has a closure that does not contain a periodic geodesic. That's the title of the paper. It's a recurrent geodesic, which is not periodic. So it's a geodesic on a surface whose closure is so complicated that it does not contain a periodic orbit. That was a remarkable contribution of Morse in 1920. Now, let me mention the following. This is Mr. Hedlund. Hedlund was a student of Morse, and he published many papers on topological dynamics, symbolic dynamics, and there is a huge controversy, once again, whether or not Hadamard created symbolic dynamics. Many people claim that Hadamard was only a geometer and was not interested by dynamics, which is ridiculous. So people say that in order to create the field, the dynamical field symbolic dynamics, you would have to discuss dynamics, and that was not the case of Hadamard. And Hadlung himself claimed that his master, Morse, was not interested by dynamics, but only by geometry, which again is not true. Anyway, many people claim that the founder of symbolic dynamics is Hadlung. Let me go on with a more recent paper. It's a paper by Gromov, which essentially it was not published. He wrote this paper in 1980, maybe 79, but for some reason he never published it. At the time, he was writing so many good papers that when the referees were sending comments, he would not take time to take into account the comments of the referee, and he did not publish the papers which were not accepted immediately. So this paper in 2000, so 20 years later, was published by the good idea of Pierre Delard. He had the idea of asking Gromov, well, please give me your old unpublished papers. I promise I publish them. And he published this paper on l'enseignement mathématique in 2000. So let me tell you what is the content of this paper. The first observation of Gromov, he claims in the first paragraph of his papers, of this paper, that no idea is due to him and everything is due to Birkhoff. Maybe this is true, I don't know. The first observation of Gromov is that if you take geodesics on the pair of pants, as I told you, this is encoded by a shift, the shift map on symbols. Now, on a given surface like that, you can put many metrics with negative curvature, not only one. And the theorem is that all of these geodesics, or all these metrics, are coded by the same object, the same shift. Therefore, the geodesic flow on negatively curved surfaces up to topological equivalence is independent on the choice of the metric that you have on the surface. That's a remarkable consequence. You take a surface, you put two metrics with negative curvature on it, you get two geodesic flows. Theorem, they are equivalent by some homeomorphism. So the dynamics is independent on the choice of the Riemannian metric on the surface. And the contribution, I will tell you more, the contribution of Gromov is that what is important to understand the dynamics is not the Riemannian metric, is not the surface, just the fundamental group. Gromov is able to reconstruct the geodesic flow of a manifold with negative curvature just looking at the fundamental group. So let me explain the idea. Consider a compact manifold with a Riemannian metric with negative curvature. Okay? Now, as you know, when you take the universal cover of the manifold, it's homeomorphic to a ball, and this can be compactified by some boundary, which is a sphere. Now, if you take a geodesic in the manifold M, and if you lift it to the universal cover, it goes from one point at infinity to some other point at infinity. And if you take a third point on the boundary, you can project it here on the geodesic, and you get some kind of origin. So in such a way, you can identify the unit tangent bundle to the manifold M tilde to triples of points on the boundary. And that's a way of saying you can forget about the manifold. The only thing which is important is the boundary of the universal cover. And from that, Gromov was able to prove the following theorem. Suppose you have two compact manifolds, M1 and M2. With negative curvature, both. Suppose that the fundamental groups are isomorphic. But you know nothing about the manifolds, just the fundamental groups are isomorphic. Then Gromov proves, with a simple proof actually, that the unit tangent bundles of the two manifolds are homeomorphic. And not only that, there's a homeomorphism sending the orbits of the geodesic flow of M1 to orbits of geodesic flow of M2. This homeomorphism sending orbits of geodesic flow of M1 are mapped by this homeomorphism to orbits of geodesic flow of M2. So this is a remarkable theorem. You don't know the manifold, you just know the fundamental group, and then you can reconstruct the geodesic flow just looking at the group. Okay, so that's one of the theorems, three remarks. One of the three remarks is this. And then later, Gromov went much further. He said, let's forget about manifolds. Let's just think about groups. Let's forget about the geometry of Riemannian metrics. Let's look at only groups. And he created, at the end of the 80s, that's the theorem I mentioned. If two closed manifolds of negative curvatures have isomorphic fundamental groups, then the unit tangent bundle are homeomorphic, and the geodesic foliations of both are homeomorphic. There's a homeomorphism sending leaves of the first to send leaves of the second. And then in the 80s, end of the 80s, Gromov invented the concept of hyperbolic group. Has nothing to do with Riemannian geometry. There's no manifold behind that, just a group. So you start with a group, gamma, and you suppose that this group is generated by a finite set S. Then from this finite set in the group, you create the so-called Cayley graph. The Cayley graph you have a picture here is a graph whose vertices are elements of the group gamma. And you connect two elements of the group if the ratio gamma 2, gamma 1, minus 1 belongs to S. So you connect two elements of the group by an arrow, by an edge, if you can go from one to the other by one of the finite number of generators of S. You create a graph, and this graph somehow has a geometry. The distance between 2 points is the length of the shortest path connecting them. And Gromov proposed the following definition. The group gamma is called hyperbolic if it looks like hyperbolic space. And look like means what I mentioned yesterday in the letter from Gauss to Schumacher, if triangles look like Ys. So the definition is this. If you pick 3 points in your graph, if you connect them by geodesics in order to construct a triangle, this triangle has to be thin, meaning that every point from each side should be at some distance less than delta from some point of the other two sides, like on the pictures. There should exist some delta such that for every triangle, you have this picture. This definition of Gromov is very stable. A huge number of groups are hyperbolic. And the good point is that fundamental groups of compact manifolds with negative curvature are hyperbolic, but the world of hyperbolic group is much wider than groups with coming from manifolds. It's a huge world. In some sense, if you pick a group at random, it is hyperbolic. Therefore, most groups belong to the definition of Gromov. Most groups are hyperbolic. And most groups have Gromov constructed the boundary, constructed everything, and then Gromov did the following. He defined the geodesic flow of a group. No manifold, no Riemannian metric, no geodesic. You start with the group. It's a finitely generated group. It's a countable group, has a finite number of generators, has this satisfies this property of hyperbolicity, and from that, just from that, Gromov constructs a flow, a dynamical system, a geodesic flow for the group. This is remarkable. This passage, going from manifold to fundamental group is well known. But starting from a group and constructing a dynamical system is, I think, remarkable. If the group, for example, is the fundamental group of a surface, you construct in such a completely abstract way the geodesic flow of the surface. Well, I must say that when Gromov wrote the proof, many quotes of this theorem in his book in 1988, nobody could understand it. And could not understand it because there was no proof. And actually, my first doctoral student, Christophe Champetier, I asked him to clean the proof, to prove it. And he worked hard, and he got the proof of that. And I was some kind of anxious. I mean, what Gromov will say? I mean, will he accept this as being some kind of valuable for a PhD? Or maybe Gromov could say, this is my theorem. It is his theorem. This is Gromov. Huh? And the point is that Gromov was so nice that he came to the jury, to the defense. He was very nice with the student. He was completely open to sharing the theorem. Maybe I should write Gromov and Champetier here. I would not write Champetier because the proof of Champetier is not completely correct either. Okay, I'm finished. I just want to mention something, as usual, about the Morse sequence, which has been invented by Morse. This T of A is AB, T of B is BA. As usual in mathematics, it was not invented by Morse. It was invented earlier by Tu in a different context. Tu also wanted to write a sequence of letters with no cube. Why would you like to think about this problem? Write a sequence of letters with no cube. And there are many theories about that. One of them is the following. Some people claim that in some rules of chess, if you can prove that the game passes 3 times through the same sequence of moves, then the game stops. And the question that was open at the time is, does this rule for stopping the game of chess after 3 identical sequences of moves, does this rule forces the finiteness of the length of a game of chess? Can you imagine an infinitely long legal chess game in which you never pass 3 times to the same position, the same sequence of moves. And it seemed like a totally useless problem. And that was the problem that Tu wanted to solve, that he did solve. So let me quote to finish the first sentences of the paper of Tu, proving that Tu was not really an applied mathematician. His motivation is this. For the development of logical sciences, it will be important, without consideration of possible applications, to find large domains for speculation about difficult problems. This might be the definition of mathematics. Huh? This is, for me, it's totally absurd. Huh? In this paper, we present some investigations, a theory of sequence of symbols, a theory that has some connections with number theory. And then he goes on producing sequences of letters with no cube, with no motivation, except maybe this game of chess. Okay, I'm finished. I wanted to say that later, people discovered that this sequence of Morse and Tu was already known by somebody called Prouet, 1851. Thank you, 1851. This guy also wrote a very strange compte-rendu note with no motivation at all. The rule of the game is the following. Can you find 16 numbers in 2 groups of 8, such that the sum of the first group is equal to the sum of the second group? The sum of the squares of the first group is equal to the sum of the squares of the second group. The sum of the cube of the first group is equal to the sum of the cube of the third group. And he does that. And then he says, what about 32? Can I find 32 numbers divided in 2 groups of 16, such that the sum of and then he produces a sequence of solutions for this kind of problem, once again with not many applications. And he implicitly produces the sequence of Tu Morse. So this is why today this sequence is called the Prouet Tu Morse sequence. Thank you very much.